Welcome back. In this lecture, we will look at how we can implement the Butler-Volmer equation in the context of a full cell. This is very important for most of the device applications. For example, when you're thinking about a battery, the voltage that we can get from a battery if it is discharging at a particular current rate, or even a device that requires a power input. For example, it can be charging of a battery or an electrolyzer which is operating at a particular current. Okay? So this has very important electrochemical engineering application. So it's important you understand how we look at Butler-Volmer equation with taking into account both the electrodes of a full cell. In earlier lectures, we had looked at a single electrode. We had looked at a single electron transfer reaction that is like a model system that helps you understand the many microscopic features of electron transfer reaction. But in practice, most of the electron transfer reactions are multi-electron transfer reaction. So connection to experimentally measured rate data is very important to get the elements of electrochemical kinetics. So the elements of electrochemical kinetics are established by these parameters: order of the reaction, order of certain reactants, charge transfer coefficients. So the connection to experimental data is very critical to fix all these terms. That's what we had seen earlier. So again, to emphasize, we had discussed these issues in the context of a single electrode. But when you go to a full cell, there are two electrochemical reactions involved in two different electrodes. For example, to have a specific context, let's take a Galvani cell. When it is discharging, zinc gets oxidized and this compound gets reduced. Even if you take into account hydrogen addition to this compound, nickel oxyhydroxide gets converted to nickel hydroxide. So there is an addition of hydrogen, so this compound gets reduced. This chemical intuition will tell you that this is going to generate potential, as the overall reaction would be an exothermic reaction. That's why we are referring to this as a Galvani cell. So what is that we want to be doing? So the problem we would like to solve is that if this Galvani cell is discharging at a particular current, okay, you want to know what is the voltage that you can get from such a cell. Or the other way around, if you want a particular voltage from the cell, if this is fixed, the voltage is fixed, what is the current you can get from the Galvani cell? So one of them is fixed and we want to get the other parameter. Okay. All right. So these are the two constraints. So given the discharging current or charging current also, obtain the voltage of the cell. Given the voltage of the cell, obtain the current. Let's see how we can get to these two scenarios using the formalism which we developed in the previous few lectures. This is the potential map of a full cell. Okay, this is what we want to compute, but you should be able to understand what does the potential map of a full cell entail. So the potential of the cell is defined in the following manner. This is the potential of the nickel electrode in this case. That's the positive electrode. The negative electrode is the zinc electrode. The potential is defined as a difference between two quantities. Okay, so because we are talking about the potential of the cell as the difference between two quantities, we can arbitrarily assign the value of this to be 0. So it doesn't really matter. So we can give this value to be 0, and we can quote the value of the positive electrode with respect to this value. Okay, so at this point we need to appreciate that fact, and then we are going to get the equilibrium voltage of the nickel electrode with reference to a reference electrode, let's say a zinc reference electrode. Okay, so maybe there are issues with this. We can discuss this more elaborately in the discussion hour. But at this point, we are going to quote this potential with respect to the zinc reference electrode. Okay, so that because this is a zinc electrode. Okay, so that has certain simplifications, decrease the number of unknowns. And then there is an ohmic drop in the cell, which we want to find out. Eventually, what is that we want to be quantifying? This is the O potential at the negative electrode, the O potential eta, surface O potential at the positive electrode. Okay, these are the three quantities: eta Sn, ohmic drop, that is phi 2. This 2 indicates the potential in the electrolyte. So phi 2 P minus phi 2 N. Okay, that indicates the voltage drop in the electrolyte. We assume that's an ohmic electrolyte. Okay, that's a good assumption. And then we want to find the surface O potential at the positive electrode. Once all these things are found, this is a well-defined quantity. So this is an important slide which indicates all the different things which we want to be finding out. These are for now unknown. We would, in the next few slides, give you how a procedure to find out these terms. Okay, so this is an unknown, this is an unknown right now, and this is also an unknown. Okay? This is a known quantity because it's just a reference potential. Okay, and by definition, we can put this as 0. All right. Okay. Let's get started on how do we go about figuring out these unknowns. Before we get to that, we should know what are the data that are needed for generating V versus I, V as a function of I. Okay, in this case, we are going to take the viewpoint that you're given I and we want to get V. All right. So to be able to do that, we need the roughness of the nickel electrode. We had introduced the importance of roughness in a previous lecture. That can be measured. Okay, so this is an important quantity that is quantified in experiments using something called electrochemical surface area. If you're practicing experimental electrochemist, it's very important that you measure the electrochemical surface area, ECSA, very carefully. That has to be provided before we can undertake this computation. We should also know the roughness of the zinc electrode. The roughness differs and it can be experimentally measured, let's say. The exchange current density for the nickel electrode has to be provided, and also for the zinc electrode. The difference in the magnitude of exchange current density is a measure of electrocatalytic property of the two different electrodes. Again, for now, this is something that can be experimentally measured. Temperature. This is a potential that of the positive electrode reference to a zinc reference electrode. Okay, this makes the number of unknowns, decrease the number of unknowns. This is the anodic charge transfer coefficient, anodic coefficient for the zinc electrode. Okay, so for each of the electrode, the reaction can be anodic and cathodic at one of these electrodes. So you have to provide 4 different charge transfer coefficients. The 4 different charge transfer coefficients are 2 anodic charge transfer coefficient corresponding to 2 different electrodes, and 2 cathodic charge transfer coefficients corresponding to 2 different electrodes. So there's a pattern to it, as I have mentioned in an earlier lecture. The sum of the anodic and cathodic charge transfer coefficient corresponds to the total number of electrons that are transferred, right? For example, 1.5 plus 0.5 corresponds to 2. That corresponds to 2 here. Sorry, 2 here. Likewise, for nickel on this electrode, 0.5 plus 0.5 corresponds to 1 electron. That corresponds to the 1 electron transferred here. So this again is something we assume right now you obtain from some other experiment. Okay, so you have this with you, maybe from a single electrode study. And then you should know the conductivity of the electrolyte. There are many ways to measure the conductivity of the electrolyte. And then there is this thickness of the electrolyte. This is under your control. Okay, so these are the data that you need to have before you can undertake the overall computation for the potential of the cell. Let's move on. So step 1 is what you do at the anode. So what is the unknown here? This is the unknown. I know this. So if given the current density of 1000 ampere per meter square, that is the I. Okay, I know the underlying equation, which is the Butler-Volmer equation. So this is known, this is known, this is also known, this is known, this is known, this we have set it up as 0 because we are referencing the cell with respect to each other. This is also known, right? For UN is also known. So the only unknown is 5 to n. Okay, so that is the only unknown here. Okay, so that unknown shows up in both places. So because there is a single unknown of 5 to, again, emphasize 2 indicates a potential in the electrolyte. 5 to n indicates the potential at the negative electron. Okay, so that is the only n. That's the only unknown. We can get that quantity. Once that quantity is known, the surface over potential at the negative electrode is can be known. Okay, so you can get to the magnitude of this quantity. Okay, so with this equation, I can get to this value. Next, I know the electrolyte obeys Ohm's law. So just there is a linear drop in potential. Having known the conductivity and the potential at this point, I can get to 5 to P. That is the potential on the electrolyte side near the positive electron. this quantity is also known. Now, I think it must be straightforward on what should be step 3. Step 3 is use the Butler-Volmer equation to get the O potential at this point. So again, what is known? This is known, this is known, this is known. Alphas are known. So the only unknown here is phi 1p, okay? Because this I also reference this quantity is I know the equilibrium potential for that electrode. Okay, so the equilibrium potential is known. This is known. So all I need is to obtain this quantity. Okay, so that can be, we have one equation and one unknown. We can get to that. So when once that is known, I can define or quantify, it's already defined, I can quantify the surface over potential at the positive electrode. Okay, that's a negative quantity. So that is well quantified. All right. So because this is known, I know this and I know this. Okay, so that's a well established quantity now. Okay, so with all these 3 steps, okay, so what I would be able to get is to document the polarization. Okay, polarization are the eters, or the O potential, the ohmic O potential, and the 2 activation O potentials at the 2 different electrodes. Okay, so as you can see, what we have tried to do is first you compute at one particular current density. All the relevant equations for the 3 steps are known. Once you have that procedure set, you can similarly undertake the procedure for any particular current density. Okay, so as you can see, there will be a linear drop for ohmic potential. That's the nature of the underlying physics. But these have a nonlinear, that is the polarization at the 2 electrodes have a nonlinear form feature. Okay, so this is the ohmic potential, which increases linearly as the current density increases. This is the O potential at the zinc electrode, and this is the O potential at the nickel electrode. So when you sum all of them up, the O potential for the entire cell is known. So the O potential for the full cell is sum of these 3 O potentials, right? So these O potentials are losses from your what you can potentially, what you can get from thermodynamics. Thermodynamics will tell you the maximum potential that you can get from a particular galvanic couple. Okay, so that is the maximum potential. That potential can be obtained only when the polarization is 0, and the polarization is 0 only at in only one condition, when I is equal to 0. It's called the open circuit potential. At that point, the polarization of the entire cell is 0. But as the current density increases, the polarization losses, okay, also increase. All these things are loss terms. As these 3 terms increase, the potential which you can get from the cell also decreases. So that is the penalty you pay. If you operate at higher current density, the potential that you can get from the cell is going to be lesser. So this procedure is very, very important in the characterization of any electrochemical device. So you should make sure you understand this quite well. All right. So what is that we have attempted to do here? Okay. So this is a summary slide. which gives the overall potential map. Okay. So we made some we specified certain important things to make the computation easy, like specifying the reference potential of this electrode with respect to a zinc reference electrode and assigning this to be 0 so that you can decrease the number of unknowns. So overall goal was to obtain the potential map. In the second slide itself, or probably the third slide itself, we had specified the potential map, okay? But there were 3 unknowns. This was an unknown, the potential drop at the electrolyte was an unknown, and the O potential at this electrode was also an unknown. We had utilized 3 equations, the Butler-Volmer equation at the zinc electrode, wherein there is one unknown quantity, this unknown quantity. Okay, you have one unknown, one equation, you can get to the solution. And for getting the potential drop, you have the Ohm's law. And there's this third equation, Butler-Volmer equation, solved at this electrode, which gives you the value of this quantity. Once you get this quantity, we can get the potential of the cell. What you should also appreciate is that the inverse problem of obtaining the current given the potential can also be done in a manner very similar to the same procedure using 3 sets of equation, but it is just a procedure. What is known and what is unknown and what has to be solved can be slightly different. It has to be solved numerically in an iterative fashion, but in essence, these are the only equations that you need to know if you are given the potential and you want to obtain the current. Okay, so there's really no big difference between the procedure for obtaining the potential given the current or for obtaining the current given the potential. Just the slight computational complexity of solving the equations is greater in the second case, that is given the current, obtaining the potential, but the procedure is conceptually very, very similar. Okay, so make sure you understand this procedure, and if there are questions, we can discuss this during the discussion hour. Thank you.